Hello students, welcome back to the channel. We're going to be going through some more electrical questions today. And what we have today is a circuit with a inductor. And in this question, we asked how much energy is stored on this inductor. We're given in the question the current of 5 amps. We're also given inductance of 0.33 henries or 330 millihenries. And the given equation is that the energy stored in our inductor equals half of the inductor times the current squared. Pretty easy, just replace all the terms. So you're going to have half of 0.33 times 5 squared, which is 25 times 0.33 divided by 2, gives you a energy of 4.125 joules. Okay? Next question is, we're given a graph in a question. And this graph gives us the peak voltages, and it also gives us a time, the duty cycle of the time of this wave from beginning to end, which is the cycle. And we are to work out the frequency, and we also are to work out the impedance. Now, the given formulas for impedance is that impedance equals resistance squared plus reactance squared. Okay. Now, we also know that impedance equals voltage divided by current. And we also know that frequency equals 1 divided by the time period. The time period here, from the wave start to finish, is 0.2 seconds. So all we need to do now, the first step, is to find our time period and work out our frequency. All we do is divide 1 by 0.2, and we find that the frequency on this system is 50 Hertz. Once we find the frequency, we can use the reactance formula to find XC, because we want to find impedance. So we know that the reactance on a capacitor is 1 over 2 pi times frequency times capacitor. So all we do now is we're going to do 1 divided by 2 pi times 50, which is here, times the value of the capacitor, which is given in the question, is 200 microfarads. So it's 200 times 10 to the minus 6. Remember engineering notation, milli, 10 to the minus 3, micros, 10 to the minus 6. And we get an reactance, capacitive reactance of 15.91 ohms. Having this value now, we can work out impedance just by using the formula. So all we need to do now is to do the square root of 33 squared plus 15.91 squared, where 33 is given in the question is 33 ohms. We find out the total impedance is 36.63 ohms. Now we can find out the final value, which is what is our current. And all we need to do to find current is V divided by Z. All we have here is a 2.5 volts divided by 36.63 ohms. And that is your final answer. You just do that in your calculator. Now the question itself only asks for the impedance. We found it, but if you wanted to find also the current, this is all you have to do. For the next question, this is a time temperature coefficient question for a resistance. So what someone would do in a lab is to test a wire, a conductor, and they'll test how much resistance it would have as you increase the temperature. So you have delta resistance, which is a change in resistance, and you have delta temperature, which is a change in temperature. So 3 measurements were made. The first one, in a temperature of 20.3 Celsius, the resistance was measured at 15.4 ohms. In the second test, with a temperature of 39.6 Celsius, the resistance was 16.5 ohms. And lastly, the third test was with 61 degrees Celsius. What is the value of R3? So what we need to do is use this formula, which is the coefficient of temperature formula, where the difference, the delta R, the change in resistance, divided by the initial resistance. So if it's number 1 and 2, the initial resistance is 15.4, the second is 16.5. So it's the change between the two 16.5 minus 15.4, divided by the initial resistance, which is 15.4, equals the coefficient of temperature times the variation in temperature, the delta T, which is 39.6 minus 20.3. So we need to find out the coefficient of temperature first though. So what we need to do is rearrange the equation where we have, so what I've done here, I've shown in red, if this is the original formula, I divide both sides by delta T, so I have coefficient of fission now separated equals the difference in resistance, the delta R, divided by the initial resistance times the change in temperature. So we've worked out here, the change in temperature is, for between 1 and 2, it's 39 minus 20 equals 19.3, and the initial resistance 15.4. We put that into the equation, so we have the change in resistance is 1.1, which is 16 minus 15, divided by the initial resistance times the difference in temperature. And we get that the coefficient of temperature is 0.4. Now this coefficient is going to be the same in each single test. So using the coefficient of fission of temperature, we can work out R3 now, again, by substituting the formula. So we go back to the formula now. We know that the coefficient, the change in resistance equals the coefficient of temperature times the initial resistance times the delta T, which is the change in temperature. Again, using the first two equations, we get that the delta R equals 0.04, which is the coefficient of temperature, times 16.5, which is the initial temperature, times the difference between the temperature of the two, which is 3 and 2 now. So the difference of temperature is 61 minus 39 equals 21. And the resistance is 16.5, the initial. So rearrange the equation. You can have a pause, have a look at it so you can understand it better. We rearrange the equation, and now what we do, we find the difference of resistance between R3 and R2. So the delta R in this case is going to be 1.41 ohms. So we know that R3 is going to be this difference of temperature plus the initial resistance, not temperature, resistance. So what we're going to do now is 16.5 ohms, which was the previous resistance, plus the change between the two. So R3 equals 16.5 plus 1.141. So we know that this new value here is 17.91 ohms. Okay? Now for the next question. This question, we have an inductor with 500 turns. There's a current of 10 amps flowing through it, and the switch is turned on for 0.2 seconds, then turned off. Now, we want to know how much energy is stored in this inductor. So, we're given a formula where the energy stored in an inductor equals half L times the current squared. So we are given in the question the energy stored, and we want to find out the EMF and the inductance. Okay? EMF, we're given the energy. So we use the formula, we put in the energy equals half of the L times the current, which is given. We find out L. So L equals 0.75 henries. Once we find the value of inductance, we can now find the EMF on this inductor, how much voltage. We're given the formula that EMF equals minus L di dt. So we're just going to place now the L, 0.75, times the current, which is 10, divided by the difference in time, which is 0.02 seconds. So now we have an EMF of 7.5 divided by 0.002, which equals 3,750 volts or 3.75 kilovolts. Okay? Pretty easy. Take a pause and then copy the answers. Okay, here we have a circuit with resistance in series and parallel. So again, what you need to do first thing, you need to look at the circuit and say, let me analyze this circuit. Which do I need to do first? You know that parallel always comes first, because when you solve the parallel, you make an equivalent parallel resistance, you create a new circuit where you can now add the resistances in series. So the first thing was to do a parallel with 5 and 10. We do 1 over Rp equals 1 over R1 plus 1 over R2. So that's 1 over 5 plus 1 over 10. Rp now equals the inverse. So Rp equals 1 over 0.3, which equals 3.33. Redraw the circuit. So you got 10, 3.3 and 20. With this now, you can work out the total resistance. You just add them up. So total resistance is just going to be 10 plus 3.3 plus 20. This is protocol for series summation, okay? This is the method, you just add them. Whereas in parallel, you've got to use the formula. Now there's another formula that you can use when you only have 2 resistors, but I like teaching this method because you can't go wrong. With the other method, if you have 3 resistors and you try and use it, it gives you a wrong result. So you have the total resistance. All we need to do next, we want to find out current. And how do you find out current? All you need to find out current is just doing I, which is current, equals voltage divided by total resistance. So it's 20 volts given here in the question, divided by the total resistance, which is 33, gives you approximately 0.6. Now you might get different decimal places. This was done during the lesson. We kind of do it together with the group. So I try and round things up just to make it easier for students. So don't be surprised if you do this calculation, you get some more decimal places which are not included. Now, the next thing that asks for is power. And we all know that power is, we don't all know, sorry. We get to know now. So power equals current times voltage. So the current, we've worked out already 0.6 amps times the initial power, the initial voltage, which is 20. So you got 12 watts of power. Now I want to know, was given in the question, what is the voltage drop in R1? What's the voltage drop in this parallel branch? And what's the voltage drop in R4? So you have R1, R2, R3 and R4. I've already written here the values 6 volts, 12 volts and 1.98 volts. If you add these up by the rule of summation of voltages, it should be equals to 20 volts. This one's 1.98, slightly off, like I said, it's decimal places, but the addition of this is 19.98, which is very close to 20. Now, the voltage on any given resistor is just going to be the current that passes through it times its resistance itself. So VR1 equals R1, which is 10 ohms, times the current, which is 6 volts. This parallel branch is going to be the current that passes through it times the resistance. The resistance on it is 3.3 times the current is 0.6. So you have 1.98 volts. And for R4 the same. You got a current of 0.6, a resistance of 20, you have 12 volts on it. So that's finalized. And finally, I can find out what current goes through R2 and R3 simply by working out the voltage divided by the resistances. So we know that the current, when it gets to this branch, it splits into I1 and I2. The current that flows around the system is 1, it's total current, but in this branch it splits. So I2 for resistance 2 is going to be the voltage divided by 5, which is 0.39 amps. And for I3, the same voltage divided by 10 ohms, which is going to be 0.19 amps. That's the end of this question, okay? Let me just check if it's filming, so I don't want to lose time. Okay, it is filming still. So the next question is just a simple parallel series of capacitors. As this is important because you just done a resistance one. Now you're going to check that it's just inversed the way you do series and parallels. So now we have 2 parallels, and for capacitors in parallel, all you need to do is add them. So you have 1.5 and 1.10, you add them together, it gives you equivalent circuit of 15, and the other one is in series of 10. So now you need to use the reverse formula, 1 over capacitor in series equals 1 over 10 plus 1 over 15 equals 0.16. You invert it because that needs to be inversed. So it's going to be the capacitance equals 1 over 0.16, which equals 6 farads. Now you have a new circuit with 20 volts and 6 farads of equivalent capacitance. Now we want to work out what's the charge on this capacitor. The given formula is that charge equals capacitance times voltage. So all it is, 6 times 20 equals 120 coulombs. Okay, don't forget the units when you write in your exams. Now the next question it asks, what's the energy stored in this capacitor? We just done a question with energy stored in an inductor. So the energy stored in the capacitor is just half of the charge times the voltage. Whereas for an inductor is half of the inductance times the current squared. Now, charge, we worked it out, is 120. We put it in the formula. And the voltage is 20 volts given in the question. So 120 times 20 divided by 2 equals 1.2 thousand joules. So 1,200 joules, or you can write it 1.2 kilojoules. Remember that kilo, 10 to the power of 3. It's good to use engineering notation. It shows that you have knowledge and you understand what you're doing. So, the next question is a LR question, where you have an inductor. In fact, no, this is a RLC question, where you have a resistor, inductor, and a capacitor. So, RLC circuits, okay? And this circuit is interesting because you're going to have a reactance which is capacitive and also a reactance which is inductive. And for these reactances, they will cancel each other out, or they will take away from each other. So in this question, you have 5 formulas that you're going to use. So you got voltage equals current times impedance. You have that impedance equals resistance squared plus x squared square root of it. You have the XL, which is the inductive reactance, is 2 pi FL, F being the frequency, L being the inductance. And that XC equals 1 divided by 2 pi FC, again F times the capacitance. So the first step that we're going to use is the XL and XC equations to determine what is the X, the reactance. Once we determine that, we can use the next formula to find out what is the impedance, and finally find out what is the current. So XL equals 2 pi times the frequency, which is 50, is given in the question, times the inductance, which is 2. So we find that XL equals 628.3. Remember, I've done this in classroom. Decimal places may vary slightly, but this is for the students to have comprehension. Now, XC equals 1 divided by 2 pi times F times the capacitance. Now, the capacitance given here was 10 microfarads. Don't forget engineering notation. Micro is 10 to the minus 6, milli 10 to the minus 3. So you need to add that, otherwise your answer will be slightly incorrect, a million times incorrect, okay? So we get an answer of 318.3 ohms. Like I said, one cancels each other because one is leading and one is lagging. So now you got to do X equals XL minus XC. 600 minus 300, you get 310 ohms of reactance, X. You have X now, you use the impedance formula. You have been given a resistance in the question. So all you do now is the impedance equals the square root of the resistance, which is 10 squared, plus the reactance, which is 310 squared. Plug that in the calculator, you get an answer of 310 ohms of impedance. Pretty easy now. You want to find current, that's the final part. All you do is voltage, 120 given in the question, divided by the total impedance, you get 0.3 amps of current, total current that flows through the system. Now, for level 3s, we're not going to go into phases, we're not going to go into angles, but that's in the next chapter. You would work out what is the angle, if it's leading or lagging. This question is for magnetism and EMF. So basically we have a conductor, like a wire or a coil inside a generator spinning, and it's cutting through a magnetic field. In the field I have north and south. So this is the field line. Now, there's a term called magnetic flux density, is how much of these lines per meter, how much concentration of lines there is, and it's measured in Tesla. So Tesla, with the unit B here, with the symbol B, the unit is Tesla. So it's given in the question that the magnetic flux density equals 2 Tesla. The length of the wire, the conductor, it's 1 meter, and that the speed, the velocity at which it's cutting this magnetic field, say if it's in a generator and this coil is spinning around the magnetic field, it's spinning at 10 meters per second. So the formula for EMF is how much voltage or the electromotive force is generated by this action of a conductor caught in a magnetic field. And by the laws of Lenz's law, you understand that whenever this conductor cuts a magnetic field, the EMF voltage is created. So the voltage that is created in this system, when it is at 45 degrees, so this wire is not cutting it perpendicular, it's got a slight angle to it, which will reduce the amount of voltage that is transferred. The maximum transfer of voltage, of EMF, is going to be when it's perpendicular, exactly 90 degrees, it's cutting it. When it's got a slight angle, you get a bit less transfer of magnetism. And when it's parallel, you get no transfer, it's zero. So we have a formula that the EMF is going to be the magnetic flux density times the velocity times the length of the wire which is cutting this magnetic field times the sine of the angle at which it's cutting. So if we blob all the numbers into the equation, we have 2 Tesla times 1 meter times 10 meters per second. You get a total amount of 20 volts. However, you need to times it by sine of 45 degrees, which is around 0.7 something. So you get an EMF, a induced EMF of 14.4 volts. So at 45 degrees, in this condition, in this velocity, with this length, or with this magnetic flux density, you get 14 volts out of this system. However, the question asks you then, okay, so what about when it's spinning in the generator? Now it's at an angle of 90 degrees, it's perpendicular, it's at maximum transfer of EMF. You're going to get the highest voltage. So what is now the new voltage? So we work it out again, and we know that sine of 90 equals 1. Therefore, we just have 2 times 10 times 1 equals 20 volts. So the EMF at 90 degrees is 20 volts in this system. Okay? So finally, the question asks us, okay, what's the delta EMF? What's the change in EMF? All you're going to do is 20 minus 14.4. There's a difference of 5.6 volts between the two. Okay? And this is it, students, for now. This is all I'm going to give you this week. Revise and study. You got your exams coming up. I wish you all the luck. And for those of you who are not my students yet, please share, like, and subscribe.